we're turning our attention to quantitative variables and how we might describe and visualize those types of variables. This is going to feel very similar or familiar to what we've just done with qualitative variables, because largely we're doing much the same thing with just a couple extra decisions to be made along the way. With qualitative variables, remember we worked with the state variable. We built a frequency table and then further visualized that with first a bar chart and then later a pie chart. With the quantitative variables, we are going to build what we call a frequency distribution, which is largely the same thing as a frequency table. And then we're going to visualize that with what we call a histogram, which again is very closely related to a bar chart. And so much of what we cover here should feel largely familiar. So the frequency distribution again is going to be, it's going to look like the frequency table. Instead of the classes, so remember we listed classes in the state variable, we just listed Minnesota, Wisconsin, I think Iowa and North Dakota. Here we're going to have to build bins. Okay, and so this is where the big difference is that we have some decisions to make as we go. But we're going to have the bins, which are going to function like the classes, and then we will have, just like we did, the number of customers or however, whatever our variable is, however many of them fall into those bins. Just like we counted up how many were in each class, we're going to count up how many are in each bin. So I've pulled the variable hours per week watching television. We have that in that kind of data set we've been working with. And we can see we have a quantitative variable here. The number of hours ranges from, it looks like it's down by 3, that might be the smallest, up to I see 58. So we need to make some bins that this data can fall into. Now with the qualitative variable, we just pulled and said, okay, all these states were in the data set, so let's just put them all as separate classes. If we did that here, we would largely get bins that just have one entry in them, right? If we made a new bin for each of these numbers, we would occasionally, so there's at least two 39s, but largely there's only one 3, there's one 6, there's one 9. We would just have, it would look, there's 3, there's 1, there's a 6, 1, 9, 1. There, we do know 39 has 2, but we wouldn't be summing up very much, right? So instead, we're going to make ranges. So something like, 3 to 6, perhaps that's going to be one of our bins, and maybe that would have 2, and then 7 to 10 or something like that. Okay, now we have to choose what our bins are going to be. So I just wrote 3 to 6, but maybe we're going to write 0 to 5, 5 to 10, or 6 to 10, and so on. Or we could do 0 to 10, 11 to 20. Right? These are all different options of where to start building our bins, and we would continue these all the way down. So how do we decide, or why do we care about the bins? Well, to highlight why it might matter, obviously if I start doing bins 0 to 5, I'm going to have more bins by the time I get to 55 to 58 or to 60 or whatever it would be, 56. I guess is the way I'm doing it here. 56 to 60. There's going to be a whole bunch of them here. Less so if I do it 0 to 10, 11 to 20, and so on. So we have to first decide how many bins. And to highlight why that's important, I'm just going to pull up a picture. I think this is actually in your text. But here are two histograms, right? So basically the bar chart, we haven't quite got there yet, but we're going to think about also visualizing this in histograms. Now on the left-hand side, here's a case where we have too many bins, or another way to think of it is the bins are too small, as it says here. And in that case, again, most of the data, or the bins, there's so many bins that some of them have 0, a lot of them have 1, occasionally you'll get a 2, but that's not really telling us a whole lot of information. the bins are, there's too many to really summarize the data. We're just getting all of the data in front of us. Alternatively, on the right-hand side, if the bins are too large, which means there's not many of them, right? So in this case, 3, we can't summarize the data either. So in the scenario here, all I can really pull from this is that most of the data is between 20 and 80. And I guess I could say it's evenly split or relatively evenly split between the two. But there's not enough bins to get much nuance out of this. And so again, because our goal is to summarize and be able to talk about and tell the story of the data, we need to make sure that we're hitting the right number of bins to be able to do that effectively. So to help us along that way, we have a rule of thumb. And now while you're working in the homework or on the looking through the book, we'll take that more as kind of a definitive answer, or that's going to be the quote-unquote right answer. But in practice, there's a little bit of gray area here. So I like to think of it as a good starting point, and then sometimes we fudge it up or down one number of bins, depending on how it exactly turns out or visually how it looks. So that rule of thumb is based around the idea that we want to, need to wait for the iPad to catch up here. We want 2 raised to the power k to be greater than n, where n is the number of observations. So in our case, I think we have 30. We have 30 in our data set, 30 customers, and so we have 30 observations with regards to hours per week watching TV. So we want 2 raised to the power k to be greater than 30, where k is going to be the number of bins. So if we had very few observations, if we only had 6 observations, we would say, well, 2 squared is 4, that's not greater than 6, but 2 cubed, 2 to the power 3, is greater than 6, right? That's 8, which is greater than 6. So if we only had 6 observations, we'd start off with 3 bins. If we had something like 220 observations, we would have to go with 8 bins. Okay, so the number of bins is going to be dependent on how many observations we have. In this case, see, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. So 2 to the 5th is 32, which is in fact greater than 30, and it's the first time it's greater than 30, right? So obviously 2 to the 8th is also greater than 30, but we stop once we get to 1. So we want to build our frequency distribution with 5 bins. So that's the first step we have to take, is how many bins do we need? The second one is to decide where they kind of start and end. We need the data, we need our bins to stretch all of the data, right? So just like with frequency table, we were worried about collectively exhaustive and mutually exclusive, we need to worry about that here as well. And of course, that carries with it that we need the numbers, we need our bins to stretch the whole range of our variable. Okay, so I think we scanned through this earlier, and we saw a low of 3, and I think the highest is 59. It looks like, so maybe I was off there. And again, there's you'll want to be, I think that's right. With a larger data set, you'd want to use the power of Excel to help you along the way there. So we need our data to range from 3 to 59. And so it needs to span 56. Or 56 numbers. And so what we would largely do is then divide 56 by 5 and realize we need them to span 11.2 and then round up. Okay, so we would round up to 12. Now, so one way to do that, or next what we would like to do is where would we like to start them? Well, to help our minds out, we like to start on nice kind of round numbers. And so one way to do this would be to say 0 to, we could say 0 to 11 or 12. Let's do 0 to 12. We do 13 to 24, 25 to 36, 37 to 48. Is that right? And then 49 to 60. Okay, so those would be, I should have maybe done this in multiple colors, but those would be bins that would work for us. Once we've built those bins, all that's left to do is to, just like we did with the qualitative variable, scan through our list and count up how many times that value or that range of values shows up in the data set. Okay, so we would start scanning through and say, how many 0 to 12s are there? Well, as I scan through, I see a 3 and I see a 6 and a 9, and that might be it. And so if that's it, if I haven't missed one, that would be 3. And then we'd scan through again, and maybe I'm not doing this, so this is probably wrong, but 7 and 12 and 6, and I'm making these up, so don't check me on those, and 2. And so we should end up with the same. This should total 30. Again, these are not correct. But if we count correctly, those would be what's there. And that is what we call a frequency distribution. So again, it looks very similar to the frequency table. And a good way to summarize the data before us. Instead of scanning through this big list of numbers, we can quickly glance at the table. A relative frequency table, relative frequency distribution follows directly as it did with the frequency table and relative frequency table. The same thing happens here. The relative frequency distribution is just going to be, again, so this is going to be 0.1, right? So 3 divided by 30. This is going to be 0.233. This is going to be 0.4, 0.2, and 0.066, if I haven't messed up the math. And so that we can quickly glance and say, 40% of the customers watch between 25 and 36 hours of television per week. Okay, a couple other things to note. So I said the number of bins is kind of a good starting place. In practice, what I would likely do here is expand this to 6 bins. Because we're stretching from 3 to 59, it's going to feel a little more natural for us to think about 0 to 10, 11 to 20, 21 to 30, and so on, right? And so thinking ahead to what we actually are trying to do, tell that story, help the reader interpret the numbers, it's going to be cleaner for us if we're looking through this list of bins, if it instead is 0 to 10, 11 to 20, 21 to 30, and so on till 50. Well, I guess it's not that far. I could finish this out. 41 to 50, and then 51 to 60. Okay, that to me seems a little more easy to interpret. So I would at least try it out that way and see how it looks. The other thing that I want to drive home is that we have the same 2 concerns that we did with the frequency table. Remember, at that time we talked about the concepts of mutually exclusive and collectively exhaustive. Okay, and those 2 concerns carry with us at this point as well. So we need to make sure that with our list of data here, that each of them finds a home and only finds one home. Okay, so we need to make sure that all of the values in this variable find a home, right? So, and I think we have it set up that way, but so like the 29 needs to find a home here, right? And it does, it sure is. It sure does right there, right? And so we need to make sure. So how do we accomplish that with bins? Well, we would one way is we can't have our bins start at say 5, right? We need to make sure that they stretch below the smallest and above the largest. So if we started our last bin at 5 and then we had we were trying to find a home for the 3, right? We wouldn't have a home for it. So it would not be collectively exhaustive. For mutually exclusive, we need to be careful about how we set up the lines between our bins. So because these are rounded to the full number, we were able to kind of avoid the trickiest part. So our bins stretch from 0 to 12 or 0 to 10, depending on which one we're looking at. And then they start a whole number higher. But if these were all 29.62 and 46.10, if we had decimals involved, we would need to be more specific that this started at 0 to 12, and this was actually we would need to do something like 0 to 12, and then greater than 12 to 24, and then greater than 24 to 36. And the reason I bring this up is that what if we had a number specifically at 12? We would want to be clear that that falls in just one of the bins. The way we've solved it here is that we've just said 0 to 12, 13 to 24. But if there was the possibility of values of, say, 12.5 or 12.2, we can't have that space in between. And so a more correct way to write, even the ones we did, would probably be more along this lines, where we're defining which one includes the whole number of 12 and which one starts just after it. So that helps us avoid or satisfy the mutually exclusive, right? So each value only falls into one spot. So those are two things that we want to keep track of while we are building our frequency distribution, just like we did with the frequency table. So we'll be back with a video discussing how we could visualize this data with a histogram.